My name is Niyaz Ismagilov, and I work in an industrial company, and we're developing quantum computing applications. And today I'll be talking about industrial companies' perspective on quantum computing and how we see the quantum computing, what problems we see, and what challenges do we face. Okay, so first, how we see and understand quantum computing. So we understand quantum computing as an emerging industry, and it all started in beginning of 20th century with discoveries of quantum mechanics, and that field of physics developed and still developing, and up until 80s when Yuri Manin and Richard Feynman introduced their idea of using quantum mechanics to simulate the quantum world, and that was the first proposition of using quantum computing. That later evolved into developing of quantum Turing machine in late 80s, and in 90s first quantum algorithms were developed, and the most famous one is of course Shor's algorithm. Later, at the end of 20th century, researchers learned to manipulate with individual quantum particles, and that led to development of first qubits. And after that, actually, what we call now quantum race started when many companies started getting involved into quantum computing, developing devices, and by now we have four major physical platforms for developing quantum devices. These are superconducting, neutral atoms, trapped ion, photonic, and spin. Of course, there are other propositions for using different physical platforms for qubits, and these are, of course, not all the companies and research institutions that are involved. From Russian research institutions, I think we should know the four institutions, I guess. This one, and this one, and again MSU. So by now we have different physical platform, and big news late last year was introduction of IBM's 1121 qubit superconducting processor. And Atomic Computing also presented their, at least announced their quantum computer, which exceeded the 1,000 qubit barrier. They introduced a device with 1,180 qubits. Another big, that's from the point of developing quantum devices, and from the perspective of further enhancing their quality, we had big news from Google. Well, this will be a bit old one, but it at the beginning of 2023 they introduced a paper when they introduced their experiment with logical qubits. They managed to build a logical qubit, and they showed that increasing number of physical qubits involved in the into logical qubit actually helps reducing error number. This work later was enhanced, and actually I consider this one as a big news. At the end of 2023, group of researchers from QERA, MIT, and Harvard University managed to not only build a single logical qubit, they actually managed to beat a number of them, 48 logical qubits, and build a logical circuit using these logical qubits with logical operations. As far as I remember, the number of 2-qubit gates were more than 200. And what they showed is that also increasing number of physical qubits involving into building a logical qubit actually reduces the error rate. And they're building a next generation device on the base of QERA computer, and I think they will be one of the leaders soon. So these are the recent advancements in quantum computing, and we've seen that many companies getting involved in this area. And what we see now is many companies and research institutions from different fields are involved in the in quantum computing, and we can see that it's forming as an emerging. It's emerged as a individual industry. There are companies which are working with, which are developing hardware components, companies which are developing quantum computers, those who develop algorithms, software tools, applications, companies which provide cloud access, and companies which develop specialized device. They're interconnected, work together, and all of these companies are funded with governmental support and private funding. These all parts of the system are forming as a ecosystem, and we see as it emerges, and we consider it as an industry or ecosystem. So these are the companies which are involved in quantum computing. I borrowed this image from the Quantum Insider site. I don't actually know all of the companies which are present here, but I know them companies which are not here. Anyway, it just represents that there are so many companies getting involved in the building quantum industry, and it is very hot topic, and maybe we could say that it's very hyped. So among the enterprise companies working in quantum computing, we could distinguish two types of companies. First is technology providers, and the second one is technology adapters. These are just two examples of technology providers: IBM and Google. IBM, of course, being one of the leaders in technology providers. There are companies who actually adopt technology adopters. Again, these just the few companies who are adopting that technology, and there are many of them, and these are just examples. And we've seen that many companies getting involved in quantum computing, and the question is, of course, why they do that. And apparently they do that because quantum computing has a great potential. And this slide is based on the research done by BCG company, and according to BCG analysis, which was published last year, there are four potential groups of problems: optimization, simulation, machine learning, and cryptography, and all of them have their potential impact. And for example, potential impact of optimization is assessed from 100 billion to 220 billion by 2023. Similar results, similar estimations are provided by McKinsey company. They actually assessed that by 2040, the value from quantum computing will be from 600 billion to $1.2 trillion, and that's a huge amount. And that's not just the market size, that's the value that is provided by quantum computing. This value is divided equally by saving costs and producing new value. On the left side of this slide, we see the sectors of industries which are mostly impacted, and we can see that most impact is on sustainable energy, chemicals, well, which these are based on simulation, and also finance. So I'll be talking from the point of view of technology adapters, and talk more about technology adapters because we don't have many companies in Russia which provide technology. So what is the strategy for technology adapters, and why should any company get involved into developing or adopting quantum computing? So the idea is that investing in quantum computing actually bears investing in quantum computing and losing money and failing adapting technology bears less risk than not investing and missing out. So therefore, it is preferable for companies to invest. And the common strategy is to start developing applications today, so that by the time when quantum devices, which are industrial applicable, will hit the market, be able to use them and gain the profit. Typical steps are find the right people, identify cases, do some experiments, then build your roadmap, then actually achieve the quantum advantage or any profit from quantum computing. So what are the cases of quantum computing application? This slide is borrowed from IBM company. It has done a nice research. So they recognize three horizons of applications. So the first horizon, which is the next few years, includes mostly optimization and chemical simulation problems. Next horizon includes also AI, ML, and scenario simulation. And Horizon 3 involves all of them, but in a more advanced way. These are, again, some examples. Nice report done by IQM company. That's a Finnish company which develops superconducting quantum devices. They've done a nice research, State of Quantum, in 2024. Actually, it was published in January. And these are some examples of applications. So we can see that, for example, Continuum works with Airbus, and BMW, Riken, and Fujitsu work with Toyota, developing applications and so on. I won't read all of them, and this list is actually longer than it is presented here. So here are the categories of quantum computing problems that we recognize. It actually differs a little bit from the categorization that I presented a few slides before. This is our vision. So we recognize four categories. These are optimization, which is a broad range of problems from logistics to energy, network load, and optimization of devices and machines. Machine learning, our primary interest here is generative models and neural networks. Molecular modeling, examples of molecular modeling, for example, in energy industry, is catalytic decomposition of methane in order to produce hydrogen. And physical system, this category of problems involve simulating physical world. This usually simulating real world usually usually means solving differential equations, which usually reduces to linear systems. So I'll talk a little bit about optimization problems. This actually is, as we have seen, optimization problems lay in the first horizon, and we also see them as problems which could provide benefit earlier than other types of problems. And when we talk about quantum optimization, we should talk about QUBO problems. QUBO stands for quadratic unconstrained binary optimization. And from what the name states, actually, it's an optimization problem with binary variables and with no constraints. And there is also Ising model, and you all know, being physicists, what is Ising model, and they actually are equivalent. And Ising minimization problem can be converted into QUBO problem, and these types of problems are very convenient to solve on quantum devices, and most of optimization problems are actually mean that we have to reduce the computational problem to solving QUBO problem. These are some examples of problems that are being solved, that were solved. First case is ExxonMobil. They actually have a fleet of LNG tankers. LNG is a liquid natural gas. And the goal is here to build the logistic plan, and so that no stations of LNG stations do not accumulate too much gas, and no of them stays free of gas. So they managed to reduce that problem to QBO. They applied QAA and VQE to solving this problem. This is actually the reduction. And they applied VQE and QAA. They had different ways to reduce problem to QBO. And the results were not very good. They actually didn't couldn't decide which method of reducing QBA problem, the actual problem to QBA is the best. And they had not very good performance in VQE and QAA. Second example is from Aramco. This result is from last year, if I remember that right. Oh, actually, that 2021, the first result was, but the final result was introduced last year. So the problem here, that this is the seismic problem. And in order to briefly explain how that works is we have a source of seismic waves. Usually this is some type of explosion, and we have a receiver which records the waves that return from these interfaces. And when we receive, we have this type of line, or we call it seismogram. We can say it is a function. When we have multiple of the source and receivers, we have they actually produce traces which are aligned along the hyperbola. And the seismic problem is to align them. So when we have a perfect layers, and when these wavelets are aligned along the hyperbola, and we can easily fix them in order to produce to get this type of image so that traces are aligned. This is the seismic step. We will not get involved into much detail, and we just need to know that this has to be done. When we have some non-uniformities like these curvy layers and so on, we get these wavelets are not aligned according to hyperbola, and we get this type of misalignments. And the problem here is to convert this type of alignment into this type of alignment. So this is the optimization problem. So what they have done is they developed a QBA formulation for this problem. They first developed a toy model, which you can see here. They tried on toy model and it worked nicely. They developed this QBA formulation and solved on a D-Wave device, D-Wave quantum annealing machine. And then they tested their program on synthetic oil model. So there are some open source synthetic models, Earth models, and they are actually specifically developed in order to test seismic programs and seismic methods. So they took one of them and tested and discovered that they have 3% improvement over classical in-house classical methods. So their aim was not to do something and not to perform that alignment faster, but they need to be them to align them more precisely. So they had more optimal solutions, and they have papers published here, probably, yeah, here in this YouTube channel. They have a seminar where they talk about that. But the interesting thing here is that they do not have paper on that, but they have a talk when they in a podcast. The researcher Marcin Dukalski was talking that they managed to perform to use their method in order to process their actual real data, and seismic data usually weighs a lot, so it takes a lot of gigabytes, and they managed to perform computations on real data and build real image, and their seismic specialists are working with that. So some of the examples of optimization problems. The first one is drilling rig logistics problems. So shortly, we may have several well pads. So well pad is a group of wells that are usually drilled together. So we have well pads located at different geographical locations. There may be many of them, like around 200, and we have drilling rigs which actually drill the well pads, and there are much less of them, around 20, and they have to travel from one well pad to another well pad in order to. The first constraint is we need to arrive at the time when the well pad should be drilled. So we have to guarantee that the schedule of drilling should be consistent. Then in this problem, we need to minimize the total travel distance of drilling rigs, because it's a huge device and it costs much to move them along between the well pads. And so the optimization problem is to reduce the total travel distance of all the drilling rigs. Another problem is again optimization problem. This is a multi-blending optimization problem. We have an oil refinery unit, and when the oil refinery is a staged process, and the final step is actually blending components into final product. So final product is gasoline and different types of gasoline. And the problem is to schedule the blending of components into producing final products. Blending is simple, just we pour different components and blend them and produce the product. So the problem is to make the schedule of this blending. And the constraints are we are given the total amount of products we need to produce, so amount for each product, and we have limitations of components that we have. And here we don't actually have any optimization problem. We just need to build the consistent schedule so that we have the minimum so that we can complete the actual program. So I talked about optimization problem. Next group of problems is physical system simulation problem. Of course, one of the most popular tools to do physical simulation is HHL algorithm, and it is widely used to solve linear systems. And again, linear systems appear when we work with differential equations. When we simulate systems which are described with differential equations, they are used to linear systems. And one of the examples of application of quantum computing into simulating physical systems is a computational field fluid dynamics problem, which was presented in a Airbus quantum challenge. So the challengers were given a profile of wing. You can see it, and they need to use open source CFD simulator and apply quantum computing in order to provide some efficiency. And many companies and teams were involved, and the winner was Origin Quantum from China. By then, they were not a very big company, but today they're actually famous. They even have their quantum CFD software tool. They produce quantum devices. Just this year, they announced their 72 qubit device. So yeah, they won this challenge. They have developed application, or they integrated HHL into the SU simulator, so that the conventional open source COD simulator uses HHL in order to solve linear systems, which again are part of PDE solvers. Then there is another approach to working with differential equations, especially when the differential equation is a wave equation. There is a nice paper by Costa, which actually describes how the wave equation can be reduced to Schrödinger equation. When we do that, we actually can use just the evolution of quantum state. Instead of solving a linear system, we reduce to Schrödinger equation and then just use the evolution of quantum system. We simulate the evolution of quantum system in quantum computer. So again, a nice example is application of that approach to a seismic problem, because seismic involves solving wave equation, and wave equation can be reduced to Schrödinger equation. And we consider full waveform inversion problem, which is an inverse problem where the forward problem is wave equation, and the aim is to compute or identify the speed model which underlies this equation. Sorry. This example actually demonstrates how that can be applied. I'll explain just the right side of the slide because the left side is quite complicated. So this approach was used to solve wave equation and the inverse problem. The upper right image is graph is solution of the full waveform inversion problem on a classical computer with classical methods. So this is how the classical program works. Here the black line is the true model that was used to model the wave propagation. Blue line is the initial guess of that black model, and the red line is actually a result of classical program optimization, so the restored speed model. And below we see that the same result obtained by quantum algorithm and quantum software, which was performed, of course, on emulator of quantum device. And we see that, again, the lines are the same and the colors match and lines match. And we see that quantum device actually performs, or quantum algorithm performs quite well. Seismic specialists consider this result very good, and they say that these two pictures match each other very well. So these were the several examples of quantum computing problems that appear in industry and the approach that were used to solve them. And now a few words on the challenges that industrial companies or enterprise companies face when working with quantum computing applications. First, I would like to say that there is a term, quantum supremacy, which is actually very desirable. And usually when we talk about quantum computing, we aim at quantum supremacy. We would like to we aim at developing solutions that are that fast that classical computers can solve. So we try to achieve quantum supremacy. From our point of view, we need to make an intermediate step, which we call quantum value. This is not a widely used term, but more our internal term. And what do we call quantum value? So quantum value is a state when a quantum solution actually provides value for business, and that's not a very straightforward, a very simple thing to understand. Because when we talk about quantum supremacy, we necessarily would like to achieve quantum device solving problem much faster than or much more efficiently than a classical computer. But when we talk about quantum value, we actually require a quantum solution be to work approximately at the same speed, to work approximately at the same with the same value. Cost in developing approximately same effort, and usually these applications work with quantum emulators without actual quantum devices. And when we build such a solution, these solutions start becoming interesting for business, because for business, it doesn't really matter how the problem was solved. You can use like 1,000 people using calculators to solve the problem. If that costs not very much, that is efficient for business. So in that perspective, if we build solution that costs pretty much the same as the classical solution, works as good as the classical solution, and it works with emulator, and that undermines that later we could plug a real quantum device and get a radically different quality of solution, that actually becomes interesting for business, and that produces value for business, and that helps business to make investments in this area. So this is this state quantum value actually what we are aiming at, and what solution, and these are solutions that we're trying to build today. And what are the challenges in quantum computing and adopting quantum computing solutions in Russia? So the first problem is shortage of quantum workforce. This is a global problem, and it is very acute in Russia, especially. I've been working in this area for a couple of years, and I could say that most of the people work in this area. And my discoveries are that we have a couple of groups and people working in physics, in developing quantum devices, and not that many people working in algorithmic area and developing applications. So this is a huge challenge if you decide to develop an application. It's very difficult to find a group that actually could build you one. Then there is, of course, a big challenge is lack of access to quantum devices. Well, a few years ago, we had actually also chance, and we actually communicated with Western companies who were the leaders in providing quantum computers. But no, we don't have that option. But instead, we have Russian quantum program, and there is Chinese companies who are quite successful in developing devices, and they are actually ready to collaborate and provide access. So there are some problems, and there is challenge, but it's not solvable. Still, we'd like to get better access to devices. Then there is developing quantum applications. There is strong competition with classical algorithms. Personally, we had couple of projects that we stopped just because we either discovered a very efficient classical algorithm or have developed one, and we understood that continuing this project and trying to build a quantum application doesn't have any sense, and so we had to stop. And classical algorithms are still developing, so there is a big challenge with them. Then in Russia, we are lagging behind in ecosystem development. As I shown earlier, the quantum industry is a sort of ecosystem where different parts work together, and we in Russia, we are lagging behind a little bit because not very groups work together. There are not many companies working in this area. Not very many devices are being developed, and not very much of collaboration. well, we are working with different industrial companies. We communicate with them, and still we see that even enterprise companies are not very keen to work together. This is something that we have to overcome. So these are the actually the ways how the first challenge is being overcome. There are different types of, well, it's in all world, different types of forums, challenges in hackathons. Recently, last year, the end of last year in Russia, we had one of the hackathons in Nizhny Novgorod. These are, according to, again, the Quantum Insider, top 12 universities in quantum computing. Again, these are Western universities. And I guess there should be USTC because it is a very strong university. Yeah, here's USTC, number 8, Chinese university, very strong university. And a few words on accessing quantum devices. I've already told that that's a big challenge, and I didn't tell much about specialized devices, but we discovered two types of devices: universal quantum computers, which are actual gate-based. These are superconducting, ion trap, cold atoms, etc. And there are also specialized devices, and we pay special attention to special devices because they are closer to being practical, closer to providing quantum value. And among these devices, of course, you can see here a D-Wave device, which we consider as not a quantum computer, more well, it actually implements quantum annealing. And it's not universal, and we consider it as a device that helps actually solves Ising minimization problems. So it's a specialized types of device. Other devices are a coherent Ising machine, emulated annealing, and digital annealing, and so on. So by now we can say that we can formulate actually our demand for quantum devices. We say that today, in order to do meaningful experiments, we need at least 12 qubits, and these are error-free logical qubits. We prefer to do experiments with 35 to 30 qubits, and future demand may start from 100 error-corrected qubits. Again, this is error-corrected qubits, not physical ones. And we can say that for industrial problems, solutions that we've developed, we need at least 10 to the power of -9 accuracy, and we need more than a couple of dozens of billions of gates, quantum gates, well, quantum steps to that long quantum circuits we have. Then we also have demands for specialized quantum devices. The minimum number of spin qubits required for prototyping is 1,000. We prefer to work with 20,000. Today, emulators can provide up to 10,000. 20,000, not so much. They work not very good at this scale. But the future demand, the future demand is up to 150,000 spins, and maybe even up to million. But right now we see around 150,000. So that was my last slide. Thank you for the attention. If you have questions.
Thank you. Questions, please. Maybe in Zoom?
Yeah. Let me turn. I think
Colleagues in Zoom, questions? Well, so far, I have one. You mentioned, along with quantum computing, you mentioned machine learning, yes, technologies. Yes. I wonder, how do they intersect? Are there any, well, I think they are, but how efficient it is to join them? So does quantum computing provide any additional efficiency for machine learning? Is it
Okay.
developed?
I don't know very much about quantum machine learning. Well, basically because we do not work in this area yet, but we're planning to start. But there is problem with machine learning in that usually in machine learning, in order to train model, we have to process a lot of data. And today's quantum computing is about performing a lot of computations on small data rather than small computations on big data. So, machine learning is about performing small computations, especially neural network training, small computations on big data. We just need to process a lot of data. But I know that there were publications about using quantum computing in order to produce in building generative models, the MIST dataset with handwritten numbers, and researchers from, as far as I remember, Zapata, they managed to use quantum computing and neural networks in order to build generative model to generate these handwritten digits. So what they have done is they used parameterized quantum circuit in order to produce the initial distribution for the neural network. So usually in neural networks we use either uniform distribution or the Gaussian distribution as an input data for generating models. And they discovered that if we provide initial random samples, random data for neural networks produced by quantum circuit, they claim that enhances the quality of images that were generated by the classical neural network. So neural network is classical, but the quantum circuit is used to generate the initial distribution for the neural network. Similar work was done with the empathy. They have a group of researchers led by Oleg Astafyev. They did the similar thing, but I haven't seen the paper, but I know they work in this area.
Thank you.
My student also working on the problem of classification of MIST dataset, and seems that his result is better than already published and quite close to classical analysis. And it seems that it will scale better. So if you work with very large images, then probably it will work better than classical. Not for sure, but it seems good.
So the problem is similar as to find bound state for skin glass. Same problems.
A question from Mikhail? Yes. Please.
Yeah, thank you, Niyaz, very much for a very cool introduction and broad overview of what is going on. But could you give some more details on how does it work in Russia? So because you mentioned several companies, but now we know that the bigger companies and the company where are you coming from? So how do they interact into the market? And what is this is the first question, what is the interest of this big company, of Russian big companies? And second, are there any kind of activities for building up the community and the collaboration network? Maybe a bit more social type of question rather than scientific.
Okay, I'll answer the second question first. As far as I know, there isn't any community or the consortium or a thing like that in Russia that would unite companies. There is a consortium that was built by the in the frame of a Russian quantum program, which is called I forgot the name, but the company is
A
called
roadmap, maybe.
No, yeah, in the field of this, in the frame of this roadmap, they built actually a consortium, but it includes just universities, and I don't know what they do. I'm not sure if they do much. But you're right. Well, if you say that there should be a consortium or a unity of the researchers and developers and adopters, I agree with you. It should be done. We actually work in this direction, but we as an industrial company mostly work with industrial companies or the enterprise companies in order to create such a consortium. But enterprise companies in Russia started getting involved in this area just like a year ago or so on. So their interest is just emerging. So not many of them, and I believe that soon there will be more of them. And could you please repeat the first question? I accidentally forgot it.
I don't know. It was maybe a bit vague. So the idea was, yeah, exactly like the big company, these giants like Gazprom or Sber. So what are they aiming for? So what is the big what is their interest to get their own kind of a technology of quantum computing, or how?
So there are
Just to make proper investments, let's say.
Yes. So as I told in my presentation, there are two types of companies: technology providers and technology adopters. So in Russia, enterprise companies lay in both categories. So there are companies which are interested in providing technology, and there are companies who are interested in adopting technology. So both of them, but not many of them.
Mm-hmm. Okay, thank you.
Any other questions? Maybe we could scroll. Are there any hands raised?
The hands goes first.
Okay.
I have a question. When you talked about this logistic problem, yes, by so making routes for the ships, transferring some goods, I also recalled a problem. In my mind, it was not connected with quantum computing, but maybe it is a problem of electricity distribution. When nowadays you may have agents, local agents, which produce electricity, consume electricity, and can accumulate electricity, and they are connected in some more or less not random network, but it's all distributed. And I learned some time ago that it's a very interesting problem for math and for.
Yeah, actually, especially that problem is being considered in the field of quantum computing, but personally, we haven't investigated the problem. And so there are subtleties because not all of optimization problems can be solved. And we are currently working on discovering the types of problem which are maybe efficiently solved and which are inefficient to solve. So a very simple categorization may be if we have a linear problem, especially continuous linear problem, that problem is efficiently solved via classical algorithms. So classical linear solvers are being developed for many years, and they're very efficient, and especially on moderate size problems. We haven't investigated problems of extreme size, those very big problems, because even linear solvers may start struggling. But for moderate size problems, usually those that we face in usual enterprise problems, linear solvers for linear continuous, special continuous problems, they beat any quantum algorithm. So those that we know, and those that are available solving either through the emulators or the annealing or via Ising machines. So, but again, there are types of problems which are not very efficiently solved, can be solved with the classical algorithms, and that border when which it separates those that may be solved efficiently the classical algorithms and the quantum algorithms is not very clear for me, particularly right now. But we are working on understanding which categorizing the problems for quantum efficient, quantum inefficient. And regarding that problem, as far as I remember, it involves continuous and discrete variables. And when we talk discrete variables, of course, they are preferable for quantum devices. And with continuous problems, they are more difficult for quantum device, and because you usually need a QUBO problem is a discrete problem, and when you try to solve a quantum continuous problem, you need to discretize a continuous variable that increases number of variables, and you have a problem of proper discretization, and so on, so on. So lots of problems.
Zoom, any other questions?
Actually, I have one more.
Okay.
When you showed the slide about specialized general and specialized computers, yes, it was mentioned that emulators of specialized devices can provide some value. I wonder how it's really possible that emulator can give you something, some advantage. Is it really true?
That is a very interesting and good question, and that is what we call quantum value. If we take an optimization problem that can be reduced to QUBO, and we build a QUBO solution, we could run it on an emulator. And in that sense, we can consider this problem reduced to QUBO and solved on a emulator. Consider just another way, another classical algorithms, because it is solved on a classical computer, and we can consider it just another algorithm for faster solving another classical algorithm for solving this problem. And but there is subtlety and there's an advantage for these types of solutions, because it's not very difficult, you don't need to reformulate or develop another algorithm if you would like to substitute emulator with a physical device. So basically, it should look like plug and play. So you just, instead of emulator, you use a real device. It may be an optical device, an Ising machine, coherent Ising machine, and you just substitute your emulator with this device, and you can get a radically better result. And this actually very very closely tied with the idea that I was talking about the quantum value. So if we build such a solution, which may actually be not much faster than classical algorithm, we built a solution that works with emulator, and it's not radically faster. It even maybe a little bit slower. It may cost in developing pretty much the same money, but if we would develop such a device for business, it costs the same money. It produces the same efficiency. So it considers it as equal solution, but it has an advantage in that you can substitute the emulator with the real device, and in that case, in future, this will have radically better results. So it has the potential being radically better, and therefore it can consider that solution, the quantum inspired solution, as being preferable, because it has potential to be radically better later, not today, maybe later.
Okay, one more question.
Yeah, maybe another more technical. Why this only? So you mentioned kind of two typical Hamiltonians, and one of them is very classic standard, let's say, quantum Hamiltonian. But why not any others, including nonlinear Hamiltonians, for instance? So are they considered as being in the heart of the quantum computation systems?
Yeah, you can consider other Hamiltonians. So the problem with the solvers, because Ising Hamiltonian can be mapped on Dewey machines and Ising machines. Other types of Hamiltonians usually may be used on a real quantum device or on a gate-based quantum device, and gate-based quantum devices are not very efficient yet. Even QBO problems can be mapped on VQE and QAOA. We personally tried QAOA and VQE, and we decided not to use them. I can return to my slide with our demand. So we have problems which require thousands of variables to be solved, binary variables. If you map that onto Hamiltonian, it means that you have Hamiltonian with 1,000 variables. And if you try to solve that via VQE, you need thousands of spins, not spins, qubits on a gate-based device. So that's not accessible right now. Therefore, we decided not to work with VQE and QAOA and focus on Ising Hamiltonians and quantum-inspired optimization. Basically, well, to be more precise, we actually follow two tracks in our development. So we have long-term projects which are oriented on gate-based devices, and we expect that these types of devices will meet our demands, which I show here in 5, 7, maybe 10 years, and therefore we have not many projects in this area. And then we have projects which are short-term, which may produce value in less in a shorter time period, a couple of years, maybe 5 years, being useful. Because enterprise, especially enterprise companies in Russia, they do not tend to invest in risky projects with high value, and we need to start showing some value sooner in order to keep our work in research and development.
Yeah, thank you. Maybe a very small question, but precise. Are there any D-Wave systems in Russia available? How do you know?
D-Wave is a unique system. Nobody else develops D-Wave devices. So in Russia, there is no such machine.
Yeah, but it's commercially available, so you can.
Oh, in Russia, no. In Russia, it's not available. They banned Russia. Well, long ago, before 2022.
Okay, thank you.
In Russia, basically, we have, I've shown in a slide before, we have, as far as I remember, 6 devices being developed. We have ion trap being developed in FIAN. We have ion trap being developed in Skaltech. We have superconducting developed in MISIS. We have superconducting developed in M40. We have superconducting being developed in MGO2, and we have atomic in MGO, and we have photonic in MGO.
Okay, okay.
Any other questions, maybe?
Hello. You mentioned about coherent Ising machine, and
Yes.
and in its relation, you mentioned about the continuous variables and the discrete variables.
Yes.
Could you please throw some more light on this continuous and the discrete one in relation to the coherent Ising machine, and which one will be more preferable in order to develop a better machine?
So coherent Ising machine is which from it states from the name that it is an Ising machine. So it is a machine that minimizes Ising Hamiltonian, And Ising Hamiltonian is actually operates with binary variables. These are discrete variables. So in order to be efficient, usually we require a problem to be discrete, because it cannot handle, the Ising machine cannot handle continuous variables. It can operate only with discrete variables. So if you want to minimize discrete continuous problem, you have to discretize. Well, we know that in any computer, any continuous variable is stored as a discrete variables via discrete variables. It has some discretization. But there is a big field of research on how should you discretize the continuous variable, and the answer is not straightforward. So usual binarization, which is done when it's stored in the computer memory, may not be the best one. So short answer is for Ising machines, you'd better use Ising machines solve discrete variable problems better than continuous variable problems. But this answer is very general. Usually, to be more precise, you need to consider a particular problem. But overall, usually, discrete variable problem is preferable for Ising machines.
Okay. But you mean to say that the continuous variables can be used, but they need to be discretized first?
Yes, you need to discretize.
Okay.
Do you
Thank
hear me? Can I ask a question?
Yes.
No, actually, it's not a question, but comment about the last question. Well, I think that it's more convenient to speak about algorithms in terms of non-deterministic polynomial time of computation. And if we classify all of these algorithms, you can say that some are NP complete, NP hard, or just NP problems. And as far as I know, that quantum computation very effective in terms of solving the so-called NP hard problem. For example, the algorithm that you were listed to see some, I don't know, okay, the algorithm is задача коми-вояжера, да? Those that you were mentioned, they are NP hard problems, and it means that classical algorithm will meet exponential rise of time of calculation when we increase the number of degree, and quantum algorithm will calculate in constant time. So that's their superior of quantum algorithms. And when we're speaking why the people using Ising machine, it's because there is some, as far as I know, there is a theory or some provement that any non-deterministic polynomial time algorithm you can translate in formal, you can formulate it as Ising machine. That is why it's very popular. Yes, this is my comment. Maybe I don't know. Do you know about this something?
Thank you for your comment. I could say that as far as I know, I'm not a theorist of quantum computing, but as far as I know, for now, from the perspective of computational hardness theory, we have no proof that quantum computers can solve anything faster than classical computers. So we cannot say that there are problems which, so we can say that quantum computing framework is better than classical. Well, basically, when we talk about Shor's algorithm, we know that what we know is we haven't proved that quantum computers are faster. What we have proved is we know quantum algorithm for some problems which work fast, and we don't know classical algorithms for the same problems which work fast. But we have no proof that there are no classical algorithms that work as fast. So therefore, as far as I know, there is no proof that quantum computers work faster. And considering the NP hard problems, well, pretty much the same. We don't believe that, well, personally, I don't believe that Ising machines or Ising problem formulations or any other could solve NP-hard problems, even in P problems, in polynomial time. So that would actually mean that we would prove sort of P equals to NP problem, and I don't believe that. Well, personally, that's my opinion. I'm not a computational theorist, computational hardness theorist, and I may be wrong, but that's how I see the things.
See.
Well, more questions?
One more I would like to ask. How do you think that machine learning can help, or maybe not help, or rather complicate a problem of solving problem through coherentizing machine?
Machine learning help machine learning to solve Ising problems. How can you repeat the question? How machine learning could help solve Ising problems?
It's like how training will help or maybe not help. Because I read a paper that coherentizing machine are like have a better Boltzmann sampling efficiency. Like they can sample much faster uh, uh, due to the impact of noise rather than a normal without the injection of noise. So it can train it better, you sample faster.
Well, that is an interesting point of view, but I have to say that I haven't worked in machine learning too much. So our main focus was on optimization and physical systems. So I can't tell much about quantum machine learning. That may be true. I just don't know much knowledge in that area. Sorry.
No problem. No problem. Okay, thank you.
Oh, there are no more questions. Let's thank Niyaz again. Oh, we have one more question in Zoom.
For one, I would ask about with superconducting quantum computers. We have a huge Coulomb machine like a dilution refrigerator. Do we have demand of these devices, and do we need them in the industry now? And how much of them?
Well, as far as I know, yes, we have demand for on them. I've talked with a few teams working on superconducting devices, and yes, they have demand for them. For example, MISIs have two modern ones where they actually store two quantum chips. They have one for 8 qubits and one for 2 qubits. And they told me that they had ordered two more, but I'm not sure if they had success on receiving them. The short answer is yes, we have demand on them because one quantum chip matches one refrigerator, and if you want to make many experiments on many devices, many chips, you need many of them. We can look at the picture from IBM's Quantum Lab, where they have multiple of these refrigerators hanging on frames, and that basically says that they are working with many of them. They don't have just one; they have many of them. And more you have, more is better.